We want to derive the conservation of momentum and look at some of the properties of the conservation of momentum and some of the limitations. So we'll start off with two guys standing on ice. They're supposed to be on ice skates. That's supposed to be a sheet of ice they're on. Um, there it is, ice. So basically low friction or no friction. And the big guy's going to push the little guy towards your right. So what's going to happen? Well, the little guy's going to move back. What's going to happen to the big guy, though? He's going to move backward also. So they're both going to move backwards. The arrows are meant to indicate, the lengths of the arrows are meant to indicate their relative velocity. So the little guy, we expect, moves back a little bit faster than the big guy, and that's purely because of mass. Essentially, what's happening is that the big guy is applying a force to the little guy and causing him to accelerate. And the big guy, because of Newton's third law, is experiencing an equal and opposite force. So force on guy 2, and we'll say that this is guy 2 here, and this is guy 1 here. And just actually put that over guy 2 here. Now the force on guy 2 is equal minus force on guy 1. So guy 1 gets pushed backwards. And in mathematical terms, you have this situation here. F2 equals minus F1. All right. Also, the time of the push must be the same for both objects. And so we have F2 equals minus F1. So if I take that equation and I multiply it by a constant on both sides, I can multiply it by 3. 3F2 equals minus 3F1. It's still the same equation, except I want to multiply it by t for time. And if I do that, I get that term, force times time, which you should recognize from a previous video as being the impulse. Force times time is impulse. So the impulse on guy 2 is going to equal the impulse on guy 1. And so that will also be true. But now, what can we do with that piece of information? What's the equation for impulse? Well, let's take a look at that. And we'll say the equation for impulse is this. It's force times time equals impulse. And it equals the change in momentum, which in longhand would look like this. mv final minus mv initial. But what we had was f2t equals minus f1t. All right, so what we have to do is we have to write the equation, especially for each character. So for the first guy, we would have f1t equals m1. Now we have to specify that it's his mass, the heavy guy, times v1 final, that's his final velocity, minus m1 v1 initial, which this would be on guy 1. On guy 2, we would then have f2t equaling m2 v2 final minus m2 v2 initial. Of course, their initial velocities were, we presume, both 0. And but irregardless, we now have these equations right here. We got this one and this one right here. However, we also have this relationship. Knowing this relationship and knowing these equations, what can we do? You know, it is difficult to measure the actual force in the time of contact. You'd have to put a sensor on where his hand was pushing against to measure the force in the time. However, we know the mass. We can calculate. We can measure the mass much easier, and we can measure the velocity in a much easier way. Given this, what we can do is, if you said set these two equations equal with a minus sign, then you're correct. And so that's what we'll do. We will have a minus f1t equals a minus m1v1 final minus m1v1 initial, and we can set them equal. we can set minus m1v1 final minus m1v1 initial equal to m2v2 final minus m2v2 initial. And let's just carry the minus sign into the parentheses. It will distribute it. So we get a minus m1v1 final plus m1v1 initial equaling m2v2 final minus m2v2 initial. Now what we want to do is we want to collect initial terms on the left and final terms on the right. There's nothing wrong with this equation the way it is. It's just you can philosophize about the equation better if you have the initial conditions on one side and the final on the other. And traditionally, we put the initial on the left. So we're going to add this to both sides. Add this term to both sides, which will cancel it out here. And it will m2v2 initial, add it to this side. And we want to add this one to this side, okay, which will cancel it out there. And we get plus m1v1 final on this side. So as you can see, we're going to have both final masses on the right and both initial velocities on the left and final velocities on the right. So let's go to our equation and let's write it out. Let me write it out this way. We have m1v1 initial plus m2v2 initial equals m1v1 final plus m2v2 final. And this is the conservation of momentum equation for two particles. And so there it is. You have now to put this in words. It's always best when you try to do this, if you can put an equation in words, it means you've reached some sort of understanding about the equation. So think about it for a few seconds. And then I'll put it in my words, which hopefully are okay. So there's the conservation of momentum. It says that the combined initial momentum of all the objects in the system, and the system in this case consists of guy 1 plus guy 2. And the system is not the ice or the air around them. And so the system is only those two objects. So the combined initial momentum of the objects equals their combined momentum after the interaction. Now there's a lot of little conditions that go along with this rule. Let's take a look at them to finish up this equation. Some of the rules and the limitations. Well, any forces external to the system. Let me give you, I'll go over that briefly here. Here's guy 1, okay, he's the heavy guy. Guy 2, he's the skinny guy. Okay, well, a force external to the system would be friction. If there is friction present, it's going to take away, perhaps differently on the heavy guy than it will be on the light guy. Not because so much of their mass, which will also be true, the friction will be greater for the heavier guy, but because of the surface may be different. The surface of the ice may be different from one place to another. So friction in this case would be an external force. It does not act between the two guys. Internal forces do not change. Now why is that? Because internal forces, first of all, external. Internal forces occur only between the objects internal. And we want to talk a little bit more about that. Hopefully it won't take me too long to do that. Here's an example. Here's a bullet going through a block of wood, and it moves along, and you can see what's happening to the block of wood as the bullet goes through. The block of wood is on, let's say, a frictionless surface. Go back there, and just replay that in reverse, and there it goes. Block of wood and the bullet, and the block of wood gets dragged by the bullet. What's going to happen to the bullet? What's going to happen when the bullet gets through there? Well, it's going to be slowed down. What's going to do that? There's friction on the bullet from the block of wood. So there it is. It's going slower and slower as it goes through there. However, for every action, there's an equal and opposite reaction. So not only is there friction on the bullet from the block of wood, but there's friction on the block of wood from the bullet, and it has to point in the other direction. Friction will slow the bullet down. That very friction, this very friction, is responsible for moving the block of wood. You need that friction. Otherwise, the block of wood wouldn't move. If it were frictionless, it would just go through the block of wood, nothing would happen. And so it's going to go through there. And that essentially is the friction that moves the block of wood. That force is needed. Okay. And these are the internal forces. Now, are you going to lose energy? You bet. You're going to lose energy. But that's what exchanges the momentum between the two objects, those forces. The energy that's lost, it's amazing, the kinetic energy before won't equal the kinetic energy after, but the conservation of momentum does work. Now, if there's an external force, you have a problem. You'll lose energy and it won't work. Here's an example of external forces. I won't let this go on much longer. Think of friction, air resistance, gravity if something's flying upward. These are forces all external to the system. And by that we mean they act on one of the objects, or it acts on each object individually instead of both equally. And then internal forces are forces that act only between the objects. Example is the push or the explosive force between a cannon and a cannonball. That's another one. When it explodes inside the chamber, some of the force is given to the cannonball, and an equal and opposite force is given to the cannon. So they don't alter the total momentum of the two objects in the system, but they do result in the friction certainly results in energy loss. And I'll stop there.